You ready?
You got it.
I got this. Be great.
So I can press record now.
Where's your one?
I don't have one. He told me not to use it.
Mm-hmm.
Okay. So today we're going to start by looking at a specific function, which is y equals 2x squared plus 1 over x squared. We have the graph of it up here. And it's kind of like, I don't know, it's in like a L shape kind of thing. So I want you guys to make a prediction what it would look like up here. Maybe at like a y equals like 50. What do you think the graph would look like? Do you think it would end up like crossing each other? Do you think it would come apart? Do you think it would just kind of go to the line and just like stay on the line? What do you think would happen?
Well, it looks like they're getting closer together.
Yes.
So
They are.
maybe they would connect or cross at the top.
Okay. That's a good prediction. Let's look at it. As this thing is further away. Okay. So we're gonna scroll up. So it does look like it's getting closer and closer to the line. And then up here it kind of looks like it touches the line. So let's zoom in. And you can see that it's still not touching the line. And if we were to keep going all the way up to infinity, it would never actually touch the line. Does anybody know what this line in between would be called? I know it's the x-axis, but what do you think that line would be called in between where the graph comes together? Any idea? It is called an asymptote, which is a funny word that is kind of fun to say. If I can spell it right. Yeah. Okay. So looking at this graph, do you think that there are any other asymptotes? Yes. Where do you think it is?
The 2.
The 2. Okay, let's see. So we put in y equals 2. And it kind of looks like they're touching. But if you zoom, you can see that it's just going to keep getting closer and closer and closer to that line. But it's never actually going to touch it. So how do you think we would define an asymptote? How can you put that in your own words?
The friend zone.
Let's put it in more mathematical terms. So you're getting really, really close to something. Can't touch it. But you can't touch it, right? So the definition of an asymptote is a line that a curve, that is not curve, that a curve approaches as it gets closer to infinity. Okay, so that's our definition of an asymptote. Now, there are two types of asymptotes. As you can see, there's a vertical one, and there is horizontal. So what would the equation of the vertical asymptote be? You guys know?
X equals 0.
X equals 0. And what would the equation of the horizontal be?
Y equals 2.
Y equals 2. Awesome. Okay. So, what if I gave you another function and we didn't have the graph? So I'll give you something similar. So we're going to do y equals 3x squared plus 1 all over x squared. So when you look at this equation, can you tell me what the horizontal asymptote is? Just by looking at it, without graphing it? I know that you could graph it and see it, but do you think that you could just tell me what it is? Just by looking at it? Maybe not?
Zero.
Well, not 0.
Three.
It is 3. So there's these people in math who come before us and they do all of these different things and they notice all these different patterns and they make rules for us to make life a little bit easier. So we're going to focus on finding horizontal asymptotes today. So just horizontal. We'll focus on vertical tomorrow. So there are 3 different rules. I'm going to erase this one and give you 3 different functions. Okay. Does everybody remember what powers are? Yes. What are powers? The exponent. Awesome. So what would the power of this one be? It'd be 1. What would this one be? 2 and 2. Awesome. So we're going to use our powers to help us with the rules of finding horizontal asymptotes. So we're going to look at the top degree right here, the highest top degree, and the highest bottom degree. So in this one, which one is bigger? The top degree or the bottom degree? The bottom is bigger. So I'm gonna put that right there. I'm gonna abbreviate top degree and bottom degree just for the sake of making it easier. Which one's bigger? They're equal. Good. What about this one? The top degree is bigger. Awesome. Okay, so those wonderful math people that came before us and noticed all these patterns tell us that when the top degree is less than the bottom degree, that our horizontal asymptote, which I'm going to abbreviate to HA, is equal to 0. Okay? Now, this one gets a little bit trickier, but it's still pretty simple. So when the top degree and the bottom degree are equal, the horizontal asymptote is equal to A over B. Now what A over B is the coefficients of the highest power. So what would the coefficient of this one be? 1. What would the coefficient of this one be? 3. So in this equation, this specific equation, the horizontal asymptote would be 1/3. And over here, when the top degree is greater than the bottom degree, the horizontal asymptote does not exist for D and E. So let's look back at our example that I gave you a second ago. What would the horizontal asymptote of this function be? 3. Good. Why is that? Right? So it would fall under the category of the powers being equal. Awesome. Let's do one more. Look at a little trickier case. Okay. So if we have x plus x squared over x squared, what would the horizontal asymptote of this one be? Can you tell me why it's 1?
Because you said you have to look at the highest power on the top
Good.
and the highest power on the bottom. And
So-
the coefficients are not.
So what you're saying is because this one, just because it comes later, it's still the highest, so you still use it.
Yeah.
Cool. So it's kind of like you can get rid and not look at anything but the highest powers. So if it was like x squared plus, oops, x to the 3rd, then what would it be? So which one's bigger?
The bottom.
The bottom degree is bigger than the top degree.
Is zero.
Yeah, awesome. So the horizontal asymptote would be y equals situations where it would look like this, what would your horizontal asymptote be?
How do you know the one?
Why would it be 1?
Cause that's the,
Because
when you end up foiling it, it's
Yeah,
1
Right,
squared.
right, so if you FOIL this function, you'd end up with x squared plus stuff over x squared plus 1. So your powers are equal, even though it doesn't look like it in the very beginning. And that is all. Do you guys have questions? Yes, any with it?
Why can't the horizontal asymptote exist in that one?
I have no idea,
Okay.
because that's the rule.
Okay.
Yes.
Would it be easier when you're putting it as the equals 1
Mm-hmm.
to put the t instead of the a?
Say that to me again.
Cause you have.
Oh,
a
like
thing-
the top degree over the
Yeah.
bottom degree? Like that?
Yeah, cause I would get super confused.
It's just a variable, and it's just kinda like showing you that it's the coefficient. So it doesn't really matter what letter it is. You could say that this was L over smiley face. It's just so you know that you're looking at the coefficients, A and B. You guys have any more questions? Alright.
It is an equation, so we know it's gonna have an equal sign. What else do we know? Do we know anything about?
It's got numbers in it.
You can graph
It's
it.
got numbers in it. Okay, so can we also represent numbers with, I don't know, letters? So we could represent numbers with like X?
Whoa.
Yeah, yeah, I know, it's crazy.
Should names for me.
And then if we wanna know what we're gonna use for X, we have to have some method of showing what we're gonna use for X. So what we generally do is we denote that f of X, or a function of X. Okay. Yeah? No?
Yeah.
Okay. Next, I was wondering, do you guys remember what a sequence is? Does anybody know what a sequence is? Series of numbers, okay? So just a series of any numbers, like 1, 1, 1, 1?
It's a thing we have like, you know, a function of this thing, like mine's a function of this thing, and it's a complicated mess. I don't like them.
It's a complicated mess. Okay, so let's think of maybe a more specific sequence. Does anybody here know what the Fibonacci sequence?
Like 1, 1, 2,
Yeah.
3,
5,
5,
8.
something like that, yeah.
Yeah. Perfect. Perfect. Okay. So I want you guys to try and describe this just within small groups, just with whoever's sitting beside you. Like you're trying to tell your friend how to come up with this. So I want you, how would you explain this to your friend? If you were trying to tell your friend, oh, I have this cool sequence, how could you do that? Where you get the first one though?
That is a good question. Where's the first one come from?
You never get anywhere.
Who divided by 0?
Who did it?
Okay, so what are some of the things that we came up with? How are some of the ways that you would describe this sequence to your friends?
The first two act get a good next one, and those together.
With any other ways? No? Okay, so we know that we have to take and add these two to get the third one, okay? And then we have to add these two the same way, all the way down, okay? So let's think, how could we represent this maybe in more of a function? So we're trying to decide what we want to put in, what kind of things are we going to need to know in order to get to the next number in the sequence?
The first two that you're adding.
Okay, so we need to know the first two. So what's a way that we can write those so that we know that for sure what the first two are. What's the way we could write that? Okay, constants. Could we also write it, since we are dealing with the ordering of numbers, we use this thing called n, and n typically represents what number term we are in the sequence. And so, in this case, we're gonna use, since we're using the first term, right, we said we needed to know that. Okay, so if we say f of 1, because that's the first term, and what does that need to equal for us to get this sequence set up? What does the first term have to equal? The very first number in our sequence. Yes. Okay, and then what does the second term need to equal? Okay. So, now that we have these two, we need something that looks more like this, correct? Because we have just two numbers, but how is that going to help us make the next one? How could we get the next one from these two?
The addition of the first two.
Okay, so how could I write that?
F of 1 plus F of 2.
Okay, so if we write f of 1 plus f of 2,
Equal to F of 3.
okay. Awesome. Okay, so do we want to have to rewrite this every single time that we are trying to go all the way through? So what's maybe a more general way that we could do this, taking into account that we generally use n for whatever number term that we are? What's a more general way that we could write it?
F of n equals.
Okay.
The f of n minus 2
Okay.
plus f of n minus 1.
Perfect. Can you guys see that over the?
What?
Okay. So,
Oh, never mind. Got it.
okay, and your question?
I'm good.
Okay.
It's not a question.
Yeah, it's fine. So f of n, do you understand what f of n is representing?
Yeah.
Okay, and f of n minus 2, what could we say that represents what if we put f of 3 instead of f of n? So n is now equal to 3. So, what does that do now? Okay. Okay, and does that look similar to what we have up here?
Yes.
Yes.
Mr. Cannon, I did a different equation than Chris.
Okay.
I don't know if it's right.
Okay, what was your equation?
I had f of n plus 2 equals f of n plus 1 plus f of n. So mine's very different than his.
So, does anybody else want to look at what she did and tell me what you think about it? How similar is this to the equation that you came up with? Yes,
She's going the other direction.
she's going the other direction.
So I went backwards, she went forwards. So
Okay.
she's saying two numbers ahead of the number we're looking at is the answer on this side.
Okay.
And then the one number ahead of the one we're looking at plus the one we're looking at.
Okay. So, how does this work if we put f of 3 in again? Does it work again? So let's try this. Okay, so do we know what f of 5 is, well, we're trying to find out what f of 5 is equal to. Do we know what f of 3 plus 1 is, or f of 4? Do we have that established here?
Not until after we get it.
No, we don't. And we don't have f of 3 either. So I don't know that this one works, but there may be another way that you can write it if you keep trying to change those. Okay, so let's try this with maybe a different sequence. So what if we have the sequence So first, what we might want to start with is we need to know what is our pattern. Does anybody see the pattern?
Times 2 plus 1.
Times 2 plus 1. And does that work with all of them?
Yes.
Okay, so if you multiply 3 times 2 plus 1, we get 7. And if we multiply that times 2 plus 1, we get 15. Okay, so now that we know this, what do we have to know to start out?
1. The first one.
Okay, so how do we write that? How do we represent it?
F of 1 equals 2.
Okay, so let's write that up here. F of 1 is equal to 3. Okay, now does anybody else want to tell me what kind of equation or function that we could write that might help us develop the rest of these numbers, just as we did before?
F of n equals.
Okay, so we have f of n. Awesome.
F of 2n plus 1.
Would it be f of 2n plus 1? Or would it be 2f of n plus 1?
Probably.
Okay, so these are called recursive functions. And the reason they're called that is because we're taking our first number and we're doing something to it, some sort of pattern or some sort of regular change in order to get the next number. And it relies upon the previous term in order to create the successive terms afterwards.
Alright, thank you.
All right, guys, start with, everybody go ahead and grab a marker, grab yourself some whiteboard. We're gonna kind of go around and review some stuff from yesterday real quick. So,
What was yesterday?
that's exactly what we're gonna talk about. All right, so while you're finding yourself some space on the board, I'm gonna write up our product property of radicals that we learned yesterday. Instead of using square root of a, I'm gonna say, square root of Snell times square root of smiley face, because A and B are boring. So, all right, when we took the product of these two, we actually get what? Do I remember?
I wasn't here. I don't know this.
It will be Snell smiley face. All right. So with that in mind, all right, go ahead and now write up square root of, let's say 48. All right, so we're all familiar with factoring. Remember how to do that. Talk about stuff that we learned yesterday, how you can take the product of two numbers, all right, any two numbers, if they have square roots. It's just the product of those two numbers with the square root over both, right? So with your square root of 48, go ahead and write in the next, like, we'll say 30 seconds, as many equivalent statements as you can. All right, if you're having trouble remembering what that would be, it would be like, okay, let's say square root of 6 times square root of 8. All right, and then keep going and keep going. Try to get as many as you can. You got, let's see, 20 more seconds. Think about factors. Think about what all numbers will multiply to give you 48 besides itself in 1. That's the easy way out. 3 seconds. seconds. 5, 4, 3, 2, 1. All right. So you guys can go ahead and have a seat. All right. We'll use this here in a little bit. All right. You can take your marks with you. You can leave them there. Whatever. All right. So this is kind of a wrap up of yesterday. Kind of coming back, recalling some stuff. Something else I want to review real quick is, let's say we have square root of, oh, I don't know, 49. Should be pretty simple and easy. Can anybody just say what it is? 7, but what else?
Plus or minus,
Ah, Chris, why are you saying plus or minus 7?
because we don't know on what side it is.
Maybe anybody else got any other ideas?
Negative times negative is still a positive.
It's true, right? So negative 7 times negative 7 does equal 49. 7 times 7 equals 49 as well. So we could get 2 possible answers. All right, that kind of thing in mind, we have to realize the fact that not every number works out nice and easy for us like that, right? After all, what kind of number is the number 49? A perfect square, right? I think Chris just said it. All right, so 49 is a perfect square, all right? So maybe some terminology we're still trying to remember. Can anybody list, or should we all just go ahead and list? Let's go ahead and list like the first 12 perfect squares, all right? So if you have 1 times 1, we get, and then 2 times 2 is, keep going.
9, 16, 25, 36, 49, 64.
All right, that's good. All right, so, you guys know. All right, so that in mind, all right, we have something that happens every once in a while where we don't get a nice, perfect whole number like plus or minus 7, right? So now we have qualms, we have issues, we got to figure out a way to handle it. So with our example of square root of 48, does anybody have any ideas of how maybe we can simplify this or maybe rewrite this? Maybe kind of one of the ways that you guys did. We have a bunch of different ways, right? So some people wrote out multiple factors, right? 2 times 2 times 2 times 2 times 3. Other ways we've got 6 times 8, like we said, maybe 24 times 2. All right, so there's a lot of different ways that we could write equivalent statements. But keeping in mind our perfect squares, is there a way that we could set this equal to something using one of these? Okay, so we're gonna get there. You're jumping ahead of us. All right, that's good. That's good. Eventually, yes. So what she said is true. That is the correct answer. All right, if we're wanting to, be technical and all that. But before we get there, because that seems like random, arbitrary stuff to just say. All right. So if we don't know it's that, that's what we're trying to get to. We're trying to simplify square root of 48. So let's use what we did a second ago. All right, where we kind of use factors. We use our product property rule. All right. So what one of these numbers, one of these perfect squares, will go evenly into 48? 16, right? All right, so keeping in mind factoring, like how we've been doing, if we were to kind of use that perfect square, all right, we said a second ago that we can use our product of squares, all right, or square roots, radicals, all right, so we get square root of 16, what would it multiply by? Square root of 3. All right, but if we're trying to simplify this, all right, obviously we've got the answer right there, but why are we not done? Because you can always go a little further, right? So this one worked out nice and easy. It's all, it's a nice even number, so it's a little easier to see. So this one we kind of simplify down, we get plus minus 4. What do we have left? We have square root of 3 left. All right? So say we have some other number, we could do plenty of examples that look exactly the same, all of that. But maybe this wasn't so easy, all right? So maybe there's one way of saying, like, okay, well, how can we simplify this down? Well, we can use one of these perfect squares. All right, so whether it's maybe square root of 42, say, okay, well, which one of these perfect squares will go into square root of 42, so on and so forth. All right, but maybe, all right, if we didn't have this list or we couldn't remember what our perfect squares were or whatever, maybe there's another way of doing it. So, once again, let's just stay with square root of 48. All right. Looking at some of the ways that we have on the boards, all right, what is kind of a way that, I don't know, that we could show this, simplifying down, kind of using those factors, that seems a little long and laborious, but you get real easy numbers to work with. Where are you pointing at?
All of those little 2s.
All right, yeah, so we have square root of 2 times 2 times 2 times 2 times 3, right? All right, does anybody know what type of numbers like 1, 2, 3, 5, 7, what type of numbers?
Primes.
Yeah, the prime numbers, right? So, all right, right there we have a bunch of prime numbers listed. So once again, you know, we could say that, okay, well really this is just, you know, square root of, we don't even show that, but 2 times 2 times 2 times 2 times 3. All right, seems a little long, laborious, and all that, but how in the world do we have something like this to equal plus or minus square root 4 times, or sorry, plus or minus 4 times square root of 3?
So you can make pairs.
Ah, okay, so this is where we're heading with it. All right, so there's this idea of, okay, well, we've got these perfect, or not perfect, but these prime numbers, right? So we've got all these prime numbers. In fact, I'm just gonna get rid of this little square root. All right, but we have all these prime numbers, but somehow we've got to get a 4, all right, kind of on the outside of the square root. We know the 3's got to stay under it. But right now, if we just multiply all these up, what are we gonna get? We get a 16, and that's not 4. So is there an idea? You mentioned something. What was the word you said a second ago?
Pair.
Pairs? All right, so let's see. Chris, what do you think she means by pairs? Putting 2's together? All right, so putting 2's together, pairs, maybe a little more exact. Anybody got an idea? The way you could kind of phrase this?
Two squaring things.
Certain things, do certain, all right, so basically it's this idea of getting like terms, or not really like terms, but getting our pairs of identical numbers, right? So same 2 things popping up. After all, we are dealing with square roots. We're talking about 2 numbers that are the same multiplying together. All right, so if we got our pairs, all right, that can kind of tell us something. Did we multiply our 2 and our 2 together, and then multiply these 2, and then multiply that? Once again, that would just give us 16. So how are we going to get 4?
You square the groups.
Square the groups, maybe just do what? This times this? All right, so I know it seems kind of like a random, arbitrary kind of thing, like, okay, great, like, well, you're able to find these, you know, nice little prime numbers and all that. But you may not really remember how to do that. Okay, so some of you are already a little familiar with this, but let's assume you didn't know anything about trying to solve these things. You've seen it for the first time. So I got a little story for you, all right? Imagine you are square root of 48. Actually, you're 48, and you're locked in prison. In order to escape, you have got to, all right? You've got all of your cellmates. The only way to escape prison is for you and a teammate exactly like you to gang up together. So these guys are here, 3 gets left behind. All right? On your way, as you are escaping, you get caught up. And guess what? Or sorry, somebody catches you, you're both together, one of you gets killed. All right? So there's only one of you left. But one of your other groups, they got free too, and one of them got killed. So there's one of them left. So now you have 2 of you that are off on the run, leaving the last man still back behind in prison. You guys gang up. You are now a 4 with the last guy still at home crying in his prison cell. All right? So we'll talk about why we get plus and minus later. There's obviously, you know, we've been talking about quadratics for weeks and weeks, so there's probably something there. We know all that. So we've got 2 ways. All right, we could probably go into a 3rd way. But right now, what I want you to do is go ahead and group up just next to the person next to you. So you 2, Michelle, if you want to come up, you 2. All right? So I want you to kind of both talk about which way you like most. All right? So if you like trying to find your perfect square numbers, all right, and then happen to figure out what times that will get you the number under there, or if you like using your prime numbers, all right? So I want you to kind of think of a few things. Which one do you like most? Why do you like it? And which one do you think is easier to learn? All right, go ahead and take a couple seconds. First I can see your hands. You're getting antsy. Give me something.
No, I was
Which
gonna
one do you
ask-
like?
I was gonna ask how 48 is the maximum security prison.
Just doing bad things. Andrea, anybody? Which one do you like most?
For my one, but
Why?
you don't have to, I remember all the squares.
Okay, yeah, so it's a little more labor intensive because you gotta break 48 down to finally get all your perfect squares, or not perfect squares, but all of your prime numbers. Okay, so it takes a little bit of time, but it's probably easiest to find and make sure you get all the right numbers because you can always multiply them together. All right? So that being said, what I want you to do tonight for homework is choose either method, but I want you to create your own narrative. So you can't be cheaters and steal my jailbreak analogy, which I really stole from somebody else. But, all right, I want you to create your own short story, maybe even a song like Quadratic Formula. We all know that because of a nice little song. All right, so that's your assignment. Tell me which one you like, why you like it, and create a short story. All right?
You had 2 seconds left.
Was it an electric fence or